Okay, so now let's say you want to find polar area. So we're going to start out with a very simple rose curve, three-petal rose curve. You should recognize this by now. It's r equals sine 3 theta. Now, just to harken back, just to emphasize a little bit, we know it's a sine function because it's symmetrical about the y-axis. As a general rule in polar coordinates, if it's a sine function, it's going to be symmetrical about the y-axis. And if it's a cosine function, it's going to be symmetrical about the x-axis. So this one's obviously symmetrical about the y-axis, so it's a sine. Now, obviously, my drawing here doesn't look very symmetrical, but do pardon me, there is a reason I made this part a little bit bigger, and I didn't realize that this part also had to be a little bit bigger as well. What is the area? Where do we start when we're going to find this? Well, obviously, we're going to use integration somewhere. Now, if you were integrating a standard xy graph, right? Think about it. You would draw very small rectangles, right? Think about Riemann sums. You're basically taking a bunch of very small rectangles and adding them together. Here, obviously, I can't take rectangles. What I'm going to do instead is take these small things instead. Now, these are called sectors. Basically, just a very, very, very small arc that's connected to a center somewhere. So what is the area of this little sector here? Well, it's just half theta r squared. And remember here that r is just a function of theta. But how do we prove this? Well, let's just think about the area of this little sector right here. So if we were just to imagine that this was one part of a very large circle, right, of equal radius r. Now, obviously, it doesn't look like a perfect circle here, but let's just imagine this very small part. You could spin it around and you would make a reasonable circle. And let's say the radius would be constant, right? Obviously, the radius is not constant here, but we're just going to ignore that because remember, we're doing it infinitely small. So what fraction is this little area here of this entire circle? Let's say the area of this small sector right here was A. If we divide that by the entire area of the circle, now what we're going to do is divide that area by the entire thing, the entire area of the circle, which is obviously just pi r squared. This fraction is just going to be, if you think about it, it's the same as if I just took this very small angle right here. Let's just call it d theta, because remember, it's an infinitely small angle, d theta. Let's just say we divided that d theta by 360 degrees, or in this case, we don't want to use degrees, we want to use radians, which is going to be 2 pi radians. So let's rearrange it. Now I realize that this should actually be d area because we're taking a very small area here. But in this case, d area is just going to be pi r squared times d theta over 2 pi. So you might notice something here. Pi cancels out. So if we were to integrate both sides, we get integral of dA is equal to the integral of 1/2 r squared d theta. And then obviously integral of dA you would find, which is just going to be A. In reality, you're probably not going to have to prove this, but just knowing the conceptual way of how you get there, I find, can be very helpful. The main equation is thus just going to be this. Now you might say to yourself, well, wait, my variable of integration here is theta, right? But I only have r here. But remember, r is a function of theta. R is a function of theta. So no matter what equation they give you, right? Let's say it was this one, r is equal to sine 3 theta. R, you can write r in terms of theta, right? So if you plug this in, it's going to be sine squared 3 theta. And then I'm going to let you do that integration yourself, right? Now, if you want a hint to do it, the key is to use something called a power reducing formula. So if you don't know what that already is, go ahead and look it up online. But if you know what it is, give this a shot. Maybe leave a comment below on what you got, and I'll check your work for you.